Okay, good morning everybody. So, we have completed the kinematics of deformation and then we have started with the constitutive relationship of materials. Now, for the constitutive modeling. So, we we discussed or illustrated the concept of objectivity right, objectivity in the context of large deformations, in context of large or finite deformation, right, finite deformation, right. And we have developed, so we have seen that quantities can be related in total form or it rate form, right. So, there can be total form and there can be rate form. So, we are basically relating the kinetics measure with kinematic measure, right, kinetic measure with kinematic measure, kinetic measure is or different kind of stress measure, right, stresses, and different kind of strain or deformation measure right, measure. So, this we have seen that either we can relate the stress with strain or rate form. The rate form is important when the system is nonlinear, highly nonlinear, right, because for a single deformation there can be multiple value of stresses, right. In that case there can be multiple value of stresses. So, in that case instead of total form it is easier to use the rate form, because then the stress strain relationship will be a single valued function. Okay. So, rate form is for to retain the rate form is used for nonlinear and complex material behavior For example, if we study the cyclic inelastic behavior, right, then we have to relate in rate form. Okay. So, and we have defined several objective rates, right, Jaumann rate, Truesdell rate and other rates, right. Anyway, so depending on the material behavior, material can be a material can be can have different kind of behavior. Okay. A material can be hyperelastic, for example, rubber or elastomatic material, those are hyperelastic. Our skin, many organs behave like hyperelastic. So, if you just hold and stretch them, okay, then they will deform significant. So, there can be strain can be very large, order of magnitude may be 100% or even more. So, these are the hyperelastic examples are rubber, many human organ, right, human tissue, these are hyperelastic material, right. Then that can be and material can be hypoelastic means like which are elastic material, although material cannot be purely elastic, but we consider the strain to be below certain range. So, like, and that is where we consider only elastic part, right. So, elastic material, for example, our steel engineering material, steel and concrete, right, concrete until certain strain value, small of course strain value. And then of course, after elastic it can be elastoplastic, elastoplastic means if you go beyond certain strain level, then it will deform, right, that is that will yield, and that is what elastoplastic, and there is a separate subject to this is called elasticity, there is separate subject for that. Okay. And then you can have viscoelastic means so the elasticity, but with strain rate dependency. Okay, rate dependency. So, that is what I mean rate dependency. So, the stress is all not only, so stress is not only a function of strain, but the strain rate also. Okay. So, stress is not only a function of strain, but at the same time strain rate. So, rate of strain, it is a function of rate of strain, rate of strain as well, okay, rate of strain, that is viscoelasticity. Why it is viscous? So, the term actually rate is associated with viscous. So, if you can recall viscosity, viscosity was what? The shear stress for many fluid, if you consider the fluid behavior, we write down the shear stress as a mu coefficient of viscosity and then the strain rate. So, rate is associated. So, that is the rate, that is why it is called viscoelastic. Okay. Similarly, you can have a viscoplastic. Viscoplastic means once again plasticity, but with rate dependent. So, you can have the yield criteria, you can have all other component of plasticity, but then those are all dependent. So, plasticity is there, but the plasticity is rate dependent. So, here viscoplasticity is basically rate dependent plasticity, rate dependent plasticity, that is viscoplasticity. So, viscoplasticity is most generalized material behavior. So, I mean it is in this class it is not possible to consider all kind of things. There is a separate course offered from Department of Civil Engineering, that is constitutional material modeling. That course you can take to learn this thing. Of course, soil behavior is like viscoplastic material behavior. If you ask me, there can be example, I can tell you soil is a viscoplastic material, then even concrete can be modeled as viscoplastic. Okay, concrete can be now viscoelastic material can be modeled elastomer, elastomeric material are visco, and elastoplastic is once again the steel, concrete, those are elastoplastic material. Right? Now, in this course we will discuss, we will exclusively restrict our discussion to elastic, and maybe time permit, but I do not think this time will permit. Only we will see elasticity and we will see some plasticity, that is the aim of this course. See, what the aim of this course is not to teach you plasticity everything, but then to give the basic elements which are required to learn these subjects. Okay. So, that is the aim of this course. So, nevertheless, whatever kinetic kinematic strain measures and then whatever we have derived and shown, those form the basic element of mechanics, and you discuss irrespective of the material behavior, those all the elements will be required in order to develop the theory and solve real engineering problem. Of course, things become much simpler when you do elastic, and when you go to hyperelastic, because there are strain can be very large. So, you need to consider finite difference aspect, and hyperelastic, all these things are required, those objectivity, objective stress rate, all those things are required in hyperelasticity, but or even large deformation viscoplasticity, large deformation plasticity, but elastic and other things things are much simpler, okay, because we are discussing the engineering strain and with the engineering with the Cauchy stress. Okay. So, we assume the finite small, very infinitely small deformation. Okay. So, having said that, we will start our discussion only with elastic material, and then let us solve some problem of elasticity, and then at the end I will just tell you some problem of plasticity, some elements of plasticity as well. So, elastic material model, elastic material modeling. So, in elastic material modeling, basically we use this infinitely small strain, right, strain and Cauchy stress only, Cauchy stress, and we do not distinguish between the, we do not distinguish between the deformed and undeformed configuration. Okay, we do not distinguish between the deformed and undeformed configuration, those are same, deformed and and undeformed configuration. We do not distinguish between the deformed and undeformed configuration. So, because the deformation is infinitely small, that is what in elasticity many complexities are different. So, like first Piola-Kirchhoff, second Piola-Kirchhoff, Cauchy stress tensor, everything will be same here, because we do not distinguish. So then we basically use F sigma and this epsilon, right, F sigma and epsilon, that we can relate. Okay. Now, if you can relate, sigma is nothing but this into epsilon, that will be your constituent metal modeling, right. So, this is the tensor of rank 4, right. So, sigma I j is basically C I j k l epsilon k l, that is the, so it is a tensor of rank 4, right. So, tensor of rank 4, rank 4. So, elasticity tensor, right. So, elasticity tensor tensor C, and then it has 4 ranks. So, and this is the contraction operation, you can recall the contraction operation. So, it will have how many components in Cartesian system. So, in Cartesian system, Cartesian, system, right, 3D system, it has 3 to the power 4. So, basically 81 and coefficient, right. So, it will have 81 components, right. So, elasticity tensor. Now, we will see that how we can reduce the elasticity tensor there. Okay. Now, before even we go, what is elasticity? Elastic material is, see, what is elastic material? Elastic material. So, elastic material means elasticity can be linear or it can be non-linear. Okay. It can still be linear, it can be linear elastic, it can still be non-linear elastic, mind that, non-linear. So, elasticity, the main important thing is that, but it need to be path independent. So, basically the stresses should not depend on the path of loading. So, what is important to note that this is elastic. This is elastic material model, because when you this is epsilon, this is sigma, and you see this is being loading and this is unloading path. So, loading and unloading path is same, mind that it is non-linearly deforming, mind that this is non-linearly deforming. So, it is a non-linear elastic, non-linear elastic, right. This is non-linear, but so linearity has nothing to do with elasticity, please be aware about that. However, this one is not elastic, this one is not elastic, because the loading and unloading path are different. This is loading path, this is unloading path, this is not elastic, this is not elastic, elastic. Is this elastic? Is this elastic? This is, although there is no residual deformation, it is coming to original configuration, but this is following different path, it is not elastic. See that? So, be careful. So, elasticity is associated nothing to do with linearity, rather it is something to do with the path independency. Okay. And if you can recall in tensile testing, when you do the tensile testing on steel, stress strain behavior epsilon sigma, this was linearly elastic, after that there was this thing. Okay. So, until this was the proportional limit, but there after that this first yield point and then second yield point and then this. So, if you can recall, this is the first yield point, upper yield point, this is the lower yield point. So, the point there is a, so until this it is linearly elastic, it is linearly elastic, if you can recall, but then beyond this proportional limit and then upper yield point, this is non-linear elastic, non-linear elastic. This is important. Okay. So, you see that we are considering a linear elastic material, and in considering linear elastic material, we can see that we can have sigma ij can be expressed in terms of a fourth order tensor, okay, IJK, right. Now, so basically if you write in tensor notation, the contraction operation, right. Now, what we also know, we are also aware, so we will have 3 to the power 4, so 81 component, 81 components of the constitutive matrix, right, of the stress strain constitutive of the constitutive matrix, constitutive matrix or stress strain matrix. You see. Now, the thing is that what is important to note here is that can we reduce it? Yeah, of course, what we have seen that Cauchy stress tensor in symmetric. Okay. So, but sigma is symmetric, right, sigma is transpose. So, that is that is sigma I j is equal to sigma j I, right. So, when I am writing sigma I j is equal to C I j k L epsilon k L, and when I am writing sigma I j, I can also write sigma j I k L epsilon k L. It does not really matter, right, it does not really matter. So, I can change I j, I can change j I because sigma I j and j I does not really matter. Okay. So, for that what we can see that see the stress tensor basically or strain tensor in that matter. So, sigma x x or maybe sigma 1 1 if you want to write sigma 1 1 sigma 1 2 sigma 1 3 sigma 2 2 sigma 2 3 sigma 3 3 sigma this is symmetric sigma 1 3 sigma 2 3, right. So, it is how many 9 components, right, 9 components, right, 9 components, right, it is having 9 components. So, these 9 components, because it's you do not require, because what we have seen that although it has 9 components, but then essentially for this it is a 6 component, right, because that lower triangle is basically the same as upper triangle because of the symmetry, right. So, you can concatenate it using this vector form instead of writing in tensor matrix form, you can write it in vector form the way it is sigma 1 1 sigma 2 2 sigma 3 3, and then I can write sigma sigma 1 2 sigma sigma you can write in different form, but then any form maybe sigma 1 2 sigma 1 3 and sigma 2 3, right. This is the way you can write it, right. This is the way you can write it. So, we can see instead of 9 we can have, or I will just write it like this, okay, sigma 2 3 sigma 3 1 sigma 1 2. Okay. So, essentially we can write to 6. So, then how we are going to relate it? We are going to then relate sigma 1 1 sigma 2 2 sigma 3 3 sigma 2 3 sigma 3 1 sigma. See what we are doing. First, instead of writing the whole stress tensor, I am exploiting the symmetry of the stress tensor. I am writing the stress vector. This is stress tensor, but this is I am writing as a stress vector. Stress vector. So, And what is allowing me to write in the stress vector form is that then by eliminating several component because of the symmetry. Okay. So, instead of 9 we can have a 6 component. So, I am having similarly the strain tensor I can also have 6 component. So, this is 6 by 1, this is 6 is also having 6 component, and then I can relate this to vector by linear map using coefficients, right, and that is a 6 by 6 matrix, right, 6 by 6 matrix, right. So, 6 by 6 matrix, that is a constitutive matrix of stress strain matrix, right, this is elasticity matrix. Okay. So, do you see that from 81 how we are going to 36? See, if you would have written it using this a fourth order tensor, it is 81 component, but just by exploiting the symmetry of the stress tensor I can write the 9 component stress tensor, Cauchy stress tensor in a 6 by 1 stress vector, and in that stress vector similarly I can also write I can extend the same thing for the strain tensor. So, I can have a strain vector here, and then I can relate the stress Cauchy stress tensor, I mean the stress tensor with the strain tensor with a 6 by 6 matrix, right, and that. So, from 81 to 36 you see how we can relate, we can reduce the number of coefficients, right. So, the first reduction basically exploit the. So, this is by exploiting the symmetry of stress and stress tensor, right, of stress and strain tensor. Do you see that? From 81 to 36 we can do that. Okay. Now, there is one more thing. Once again what we can see, we have seen that we can also see that say C I j k L must be equal to C k L I j, and how it is coming? This is coming because that because of the reciprocal theorem. So, economically, because if there is a you apply unit, we have all heard about reciprocal theorem, right, Betti reciprocal theorem, right, that if you apply unit load here, whatever being the deformation at other point, if you apply unit load that point deform. So, there is a positive flow of energy in the path, right, and this is reversible. So, see I j k L, whether you change I j and k L I j, it does not really change, okay, and it is a consequence of the reciprocal theorems, right. So, I j k L and k L I j will be same basically, and that can also be explained from your work done work. So, if you can recall, the work done by the stress tensor can be called work is sigma I j epsilon I j, right, that is the way you can write down, right. So, sigma I j is C I j k L epsilon k L and then epsilon I j. Now, this work done should be irrespective of these indices, right. So, here you can just k L I j epsilon I j epsilon k L, you see that. So, basically once again, so this is that is why the reciprocal theorem is nothing but a energy another manifestation of the energy conservation principle, right. So, this is the work done like stress power stress power by the stress you can write it like this, right, if you can recall, right. So, that is the way this is the power stress power, right. I have derived this thing here, of course, it is not and how there are a number of conjugate pair, here all the pairs will be same because we do not distinguish between deformed and undeformed configuration. So, this is the way. So, if that is the way, then because of the symmetry it is further reduced. So, instead of 36 how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So, it become 21. So, 81 to 36 to 21 due to symmetry of symmetry, due to symmetry of of this the constitutive matrix. The constitutive matrix must be symmetric. Okay. So, you see how we have reduced we are reducing we keep on reducing the coefficients from 86 to 81 to 36 to 21. So, from initially it was 81, then it went to 36, then it went to 21. Okay. So, first is the generalized strain the component in a fourth order elasticity tensor, then we exploit the symmetry of representation of the stress tensor, then we exploit the reciprocal theorem or energy conjugacy of the to 31. Now, we can further reduce, now we will exploit, we will see that can be further reduced. Okay. These coefficient, this constant, this elasticity constant can be further reduced, reduced by using the principle of material symmetry, the principle of material symmetry. Further reduce by using the principle of material symmetry that can be used to even further reduce. So, what is the principle of material symmetry that we have to understand? So, a material is said to be symmetric with respect to some plane if with respect to some plane if is material is said to be symmetric with respect to some plane if the state of stress or deformation become irrespective if they become irrespective by changing the by reflecting irrespective by reflection become irrespective by reflecting the stress by reflecting the stress state or deformation with respect to the said plane Now, this is to explain, that means sigma I j, right. So, it is ith and z direction. Okay. So, if I am reflecting, so I am changing to I star and I star can be maybe minus I, right. So, sigma minus I comma j. Okay. So, what does it mean is that, so as for example, this is a material. Okay. So, consider that this is a plane of symmetry. Okay. So, I am putting a material elementary volume. So, it has a state of stresses. Okay. So, state of stress. Okay. Maybe in 2D it will be easier to explain, and it is like something like this. Okay. It has two stress components, sigma 1 sigma 2 2. Okay. Sigma 1 sigma 2 2 and then sigma 1 2. You see that, right? I am having this elementary block and I am considering this is a plane of symmetry. Okay. Plane of symmetry. You see that plane of symmetry. So, in this plane of symmetry, what I am doing, I am reflecting this, right. So, when I am reflecting this, if it is a plane of symmetry, when I am reflecting this, then what this sigma and all other normal stresses is not going to change, it is going to be the same, right. The only change will be that you see that. So, sigma 1, sigma 2, those things on reflection with respect to some plane, this plane is basically so then you see this sigma 1 2 become what? Sigma 1 2 star become, it is nothing but minus sigma 1 2, look that. Okay. Similarly, sigma 2 1 okay, because so you see that this is called a plane of material symmetry. Okay. So, that is the way we should explain. So, and for this plane, so any planes consider that, so you consider that that this stress so this is the basically principle of material symmetry, and then this is the way it can be explained. Now, I will use this. So, I will just see the mathematically how can. So, if a material has one plane of symmetry, such material, then this material is called a monoclinic material. Okay, is called a monoclinic material. This is called a monoclinic material. So, how we will do that? Let us see. So, I am considering that axis. So, a plane is also this plane is what? This plane is 1. I mean, if you see that unit normal to this plane is what? Unit normal to this plane is maybe x, right? X means it is 1. Okay. So, this is, so a plane can be designated by unit normal, right? A plane is also designated by unit normal, right? Designated by unit normal, right? By unit normal. So, when I am saying 1, okay, 1 is basically minus 1, right. So, when I am reflecting 1 become minus 1, okay, that is why. When I am, so I am changing its direction. So, I am reflecting everything with respect to with respect to a plane, that plane can be 1 become minus 1, or maybe instead of 1 or maybe okay. So, this is the way we just see here, maybe this is 1, this is 2, this is 3. So, when I am considering that 1, I am considering that 2 3 is the plane of symmetry, is the plane of symmetry, okay. 2 3 is the plane of symmetry. 2 3 plane is what? That 1 is the axis of symmetry, 1 axis of symmetry, right? Not axis of symmetry. 2 3 plane is what? 2 3 plane is designated by 1. So, basically 2 3 when it is axis of, I am basically I will reflect with respect to 2 3, that is the plane of symmetry. So, 1 become what? Minus 1, because by reflection 1 become minus 1 na. You see that by reflection 1 become minus 1, by reflection 1 become minus 1. Okay. So, okay, so if that is the case, then what I am going to do? So, we have seen that until now we have reduced until 21. So, we will further reduce it. Okay. So, you just write the stress strain relationship. So, sigma 1 1, sigma 2 2, sigma 2 3, sigma 3 3, sigma 2 3, sigma 3 1, sigma 1 2. Okay, that is the way it is, huh? And then I am writing it like this. Okay. Okay, right, fine. So, C1, C2 to C33, C34, C36, right. So, that is the all the coefficients, right. Okay. So, 21 constant that we have seen. Now, what I am going to do? I am going to reflect. I am considering that I am considering that now consider that 1 is a plane of symmetry. 1 is a plane of symmetry means basically 2 3 is a plane of symmetry. Okay. 2 3 is a plane of symmetry. Okay. 2 3 plane is symmetry means 2 3 means axis 1. Okay. So, then 1 must be replaced by minus 1, you see that. So, then if 1 should be replaced by minus 1, so then what we can get, what we obtain? See, once again, so sigma 1 1, so 1 is replaced by minus 1. We have seen when we are reflecting something, if both the normal stress does not really change. Why? Because 1 minus 1, 1 is replaced minus minus plus. So, that is another way of seeing this thing. So, sigma 1 1 does not really change on reflection, sigma 1 normal stress does not change, that I have explained how it is. Sigma 2 2 will also not change, sigma 3 3 does not really change. However, sigma 2 3 will not change, because 2 3 it has nothing to, I am reflecting 1 with respect to minus 1, but sigma 3 1 is changing, because sigma 3 1 is sigma 3 will be 3, but 1 will be minus 1. So, minus sigma 3 1 and this is minus sigma 1 2. Okay. Similarly, here it is epsilon 1 1, epsilon 2 2, epsilon 3 3, epsilon 2 3 minus epsilon 3 1 minus epsilon 1 2. Okay. You understand that? So, okay, this is the way it is. Now, you understand why when I am reflecting, say I am if you consider a small elementary elementary volume, right, and then we can see that 2 3 we are considering, once again go to coordinate axis 1 2 3 and 2 3 is the plane which is the plane of symmetry. So, when I am 2 3 is the, that is where I am putting the mirror. So, if I am putting the mirror on 2 3 plane, then axis 1 is reflected as to be minus 1, right. You see that x axis become minus x axis. So, 1 become minus 1. So, for that normal stress is not going to change, but the sigma 3 1 sigma 1 2 the shear stresses or the shear strain for one axis is reflecting, that is being minus. So, that is what this is being the state of stress. So, minus, you understand why this is after reflection, why this is being minus. So, we are putting a mirror along the axis of symmetry okay, along the plane of symmetry, sorry, not axis of symmetry, I am discussing the plane of symmetry. Okay. So, then once again I am writing C 1 1, C 1 2, C 1 3, and what I know that this coefficient is irrespective of this coefficient, the state if the material has a plane of symmetry, the state of stress or deformation does not really change with respect to reflection. So, I am just going to put it like this. Okay. Now, let us see that what I am getting from here and what I am getting from here. Okay. Okay. So, sigma 1 1 is being C epsilon 1 1 epsilon 1 1 plus C 1 2 epsilon 2 2 plus C 1 3 epsilon 3 3 plus C 1 4 epsilon 2 3 plus C 1 5 epsilon 3 1 plus C 1 6 epsilon 1 2, right, from the first one before reflecting. Okay. What about second one? Sigma 1 1 is equal to, okay, sigma 1, what about second one? Sigma 1 1 is what? Is C 1 1 epsilon 1 1 plus C 1 2 epsilon 2 2 plus C 1 3 epsilon 3 3 C 1 4 epsilon 2 3 plus C 1 5 minus epsilon 3 1 C 1 6 minus epsilon 1 2. Now, what we see that these two must be same. This sigma 1 1, this sigma 1, both sigma 1, these two must be same. Whatever this is, this must be same. Now, why can this be same? You see, this is associated with minus, this is associated with minus, rest of the quantities are same, right. So, how can this to be same? Now, if these two has to be same, then this is possible only if so, then C 1 5 must be 0 and C 1 6 must be 0. If these two need to be same, then C 1 5 and C 1 6 must be 0. Okay. These two must be, if this is 0, then you see that does not really matter because rest of the expression is same, right. So, what we see that for the coefficients associated with these two must be 0. This is 0, this is 0. Similarly, this is 0, this is 0. Similarly, this is 0, this is 0. However, this does not necessarily be, because you see, because sigma 3 1 is C 5 5 epsilon 3 1 plus C 5 6 epsilon 1 2, and sigma 3 1 is C 5 5, this both are negative, minus minus, this is also minus. So, minus minus will come out. Okay. So, there is no change as far as these two are concerned. Okay. You understand why, right? Because sigma 3 1 is C 5 5 C. So, whatever sigma 3 1 is C 5 5 epsilon 3 1 plus C 5 6 epsilon 1 2, and then minus sigma 3 1 is C 5 5 minus epsilon 3 1 plus C 5 6 minus epsilon 1 2, right. These two is does not really change, this essentially is same, because both side negative, right. That is what you see. I am not changing these two, okay, only. So, only this block is being 0, filled with 0. So, this side is positive and whatever this side is okay. So, now how many are 0? 1, 2, 3, 4, 5, 6, 7, 8. So, 21 minus 8 means 13. So, monoclinic material require 13 constant, right. So, 13 constant for monoclinic material, monoclinic material. Monoclinic material. So, a material which has one plane of symmetry can have 13 coefficients. So, you see the how we are reducing 81 to 36, 36 to 21, 21 to 13, a material with one plane of symmetry. Okay. Now, I am going to consider a material with two plane of symmetry. So, a material with two planes which are mutually perpendicular. Okay. I mean, you know the axis, two planes of symmetry. If it has a two plane of symmetry, then what is happening? Maybe if it has two plane of symmetry, then what is happening? This is being minus, right? Two plane of symmetry, that means here you come, one second, let me write it down, and then sigma 1 1, sigma 2 2, sigma 3 3, sigma 2 3, sigma 3 1, sigma 1 2 is equal to epsilon 1 1, epsilon 2 2, 3 3. What I am saying is that now two plane of symmetry means already this is being minus 1, this is being minus 2, this is minus, this is minus, this is also minus, this is also minus. Okay. So, you see that I can need to have all three 0. I need to have earlier these two were already there, earlier what, okay, like these two are also there, right. But now, if when I have this also symmetric, right, then what I can have? I must have, see this is also 0, right. So, I must have you understand that. So, earlier I have this block, okay, 0 for monoclinic, but now in addition to that sigma, this is also being 0. So, then basically I need to have, this is being 0, okay, this is 0, okay, you understand that. And in addition to that, I also have this block 0, right, because whatever all three are 0. So, these 3, these 3, these 3 0 and also these 2 0. So, now, so what we can see that if two planes are symmetric, then automatically the third plane. So, also see if two planes are planes of symmetry, planes of symmetry, then the other plane automatically become a plane of symmetry, automatically becomes a plane of symmetry. So, that if two planes are planes of symmetry, then the third plane is become automatically a plane of symmetry. What this means is that off diagonal terms 0, for these two blocks. So, this block is 0, this block is 0. You see this kind of material. So, what we can see, this kind of material in which the two or three planes are symmetric, this material are called orthotropic material. Orthotropic material. So, for orthotropic material, how many constants? So, from 13, where you are going? From 13, how many constants you are getting? You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. So, 9 is for 13 is for monoclinic and 9 is for orthotropic. You see that? Okay. So, a material, and then it is very interesting to see that. So, this is a orthotropic material, orthotropic material. It is important to see that the shear stress and normal stress are uncoupled here. See that when it is 0, that means you see the shear stress will produce only shear stress, the normal stress will only produce normal stress. Do you see that? So, shear stress and normal stress are uncoupled in monoclinic material or other materials. You have seen if you apply shear stress, it will produce normal stress, because if this in the cross diagonal, the first, second and third quadrant, in this quadrant whatever the coefficients, if these coefficients are non-zero, that means even if you apply some shear stress, normal stresses will produce, and then normal stresses will also produce shear stress. But if the second and third quadrants the cross terms are 0, that means the shear stresses is only going to produce shear stress and normal stresses are only going to produce normal stress. Normal strains are only going to produce normal strain. So, shear strain and normal strains are uncoupled. So, that thing however, if see in many composite material, there are material in which it is or monoclinic material in which it is if the material is not orthotropic or it does not have all the three axes of symmetry, planes of symmetry, then it can the shear stress can produce normal strain or the normal strain can produce shear stress. Okay, but this is the particular material orthotropic, where the shear and normal stresses are stress and strains are uncoupled. So, this is now. So, you see that how gradually one after another we are reducing the constant, right. So, now we have exploited all the planes of symmetry, and as a result the cross terms between shear and normal strain, shear and normal shear stress and normal strain become 0. Okay. Those are eliminated and then. So, now I am having orthotropic material. How many constants? 9. So, this is the way, you know, it is 9 constant 1, 2, 3, 4, 5, 6, 7, 8, 9 for orthotropic material. Now, the fact is that we have already exploited the conditions that all 3 planes of symmetry. Now, we will exploit the condition so of axis of symmetry. So, okay, axis of symmetry, axis of symmetry. So, once we will see the axis of symmetry. So, plane of symmetry and axis of symmetry, there is a difference. Axis of symmetry means, you know, there is a material, okay, consider this is 1 and this is 2, 1, 2. Axis of symmetry means, say I am considering this 3 is an axis of symmetry, that means this, if these 3 become axis of symmetry, then whatever actions you produce with respect to whatever actions you produce perpendicular to this 3 axis, it will not be able to distinguish between the. So, axis 3A so, axis of symmetry, symmetry of 3, that is also called as a plane of isotropy, plane of isotropy, isotropy. So, if axis 3 is a plane of axis of symmetry, then 1, 2 plane is a plane of isotropy. What does it mean? That any actions in any action which is perpendicular to this plane, it will not be able to distinguish between 2 different directions in 1, 2 plane. So, since it is not since the material will not be able to distinguish between any directions, you know, on the direction perpendicular to axis 3, that is the axis of symmetry, that is also called, it is a plane of isotropy. So, 1, 2 plane is a plane of isotropy. Okay. So, so what does it mean? Here you see that if axis 3 is 3 become an axis of symmetry, that means it will not be able to distinguish between 1 and 2. So, what does it mean? 1 and 2, 1 and 2 means see C 1 3 should be equal to C 2 3. So, what does it mean? So, C 1 2 should be equal to C 2 3, right, and C 1 1 must be equal to C 2 2. Understand that? Isn't it? And also what? If you apply shear stress, see the shear stress which involve axis 3, that means epsilon 2 3 and 2 3 1 2 3 and epsilon 3 1. So, C 4 4 must be equal to C 5 5, C 4 4 must be equal to C 5 5. What does it mean? That means you deform the material on 2 3 plane by shear stress, deform the material in 3 1 plane, because it is will be same identical, because it will not be able to distinguish between 1 and 2, right, because 3 is the axis of symmetry. So, if it is unable to distinguish between 2, that means C 4 4 must be C 4 4, C 4 4 must be C 5 5. So, you see 3 conditions. So, another 3 more conditions, 3 more conditions are coming, right, 3 more conditions are, 1 more conditions will come. So, you will see in the next class I am going to show you, because you see that C 6 6 can be expressed in terms of C 1 1 and C 2 2, okay, C 1 1 and C 1 2, okay. 1 more condition will come, that I am going to express in the next class, but do you understand until now, right. So, by using plane of symmetry and the axis of symmetry, we are basically able to reduce the number of elastic coefficients for a linearly elastic material. Okay, until now today this is, that is all, later we will speak. Thank you very much.